Talk of the day is by Danica Kosanović on extended evaluation maps for knots and embedding.
Yeah, thank you. First of all, thank you to the organizers for offering me this wonderful opportunity to speak at such an event. I've been really enjoying it. So my talk is, so here is the plan of the talk. So here are the two notions that I want to introduce. One we've kind of already seen in a couple of talks, and so it relates to the embedding calculus. So I'm actually a low-dimensional topologist, so I'm actually interested, so one of the spaces I'm interested in is the embeddings of the circle into the 3 space. And actually that's something that you can also consider the embedding tower for, and we will see it later. But actually it turns out that there is a completely different construction that appeared maybe a bit earlier in the low-dimensional topology that you can relate the tower to. I'll summarize. Hopefully we'll get to this result of work in progress with the Shi and Peter Teichner. And I hope to explain this geometric trick that lies really at the heart of the argument. So I'm not avoiding geometry or topology. Okay. So here's how it started. So I'll start with, so my goal is to explain what a grope cobordism is. But first I'll introduce some motivation, how this notion actually appeared. So Vasiliev in the 90s introduced this theory of finite type invariants. What he considers is this space, so I'll consider the space of long knots. So I see them as the embeddings of the interval into the cube with the endpoints fixed. And so what he did is he actually considered the space of all immersions and the complement of embeddings in immersions. And he was able to filter it by such a filtration. So if you're familiar with this, you can maybe remember what this is, but if you're not, I'm actually not going to talk about it. What I'm interested in is the dual description, which looks like this. So there is a certain tower of, I'll say later what. It starts with so I'm considering pi 0 of k, right? So this is the isotopic classes of knots. And it's actually a abelian monoid with respect to connect sum. What you can do is you can introduce this relation of n equivalence, and that's where the word grope cobordism appears. Actually, more precisely, it should be simple capped grope cobordism, but for the purpose of this talk, I'll define it later. And I'll call it capped grope cobordisms. And this is where the degree n appears. So you have one of these for each n starting from 1. Okay, and what I mean by dually is that there is this theorem by various people, including Gusaro, Habiro, and Conant-Teichner, which says that 2 knots share the same invariance in this sense of Vasiliev of type at most n-1 if and only if they're equivalent in this geometric sense. Okay? And what turns out is that these are actually finitely generated abelian groups. So remember, knots don't have inverses, but when you introduce the relation, you somehow get the inverses. That's what is interesting. However, we don't really understand these groups. So that's somehow my motivation for studying them. What else? Well, there is also this descending filtration where, well, I still haven't told you what this n equivalence is, but stay with me. So we can consider knots which are n equivalent to the unknot, and then there is such a filtration. And what's interesting is that if you take the n minus first subset in this filtration and you quotient it by this n equivalence, you get a group, and there is such an isomorphism. So what we have on the right is a certain space of diagrams that I will explain. So somehow in a way they relate to these graph complexes as well. The theorem of Kontsevich was to construct such a, so Z are usually for partition functions, so somehow comes from this physics intuition. And the map in the other direction is a certain, rationally, this realization map that I will also describe. Okay? So what are these spaces? So we can define this A and -1. I stands for indecomposables. So I'm not interested in the most general case. What turns out is that you can describe it in many ways. So the first that maybe chronologically appeared was the score diagrams, where you just So what is this? So this is just a data of pairs of points ordered somehow on this interval, right? So note that these intersections here, these crossings don't matter, so don't care about them. So this is just a graph with this information of how it connects to the line. But if you consider more complicated graphs with trivial invertices, and also you can allow loops, but you allow only the trivial invertices, and you also have this information of how these univalent blue vertices attach to the line. That's what I call here Jacobi graphs. And they appear naturally in this perturbative quantization story. You here have to quotient by some relations, but I won't present those because I'm actually interested in this third space of diagrams, okay? And that's where this n-equivalence naturally lives. So these are just trees. I don't allow loops, and I don't allow many, so it's just one component. So when you forget this line, this black line, which you should think of as a unknot, then it's just a tree. So a connected graph without loops and trivial invertices. Okay. So here it's again, I copied this, and I just wanted to present how one of these relations look like. So before introducing this relation, you somehow can relate these graphs to the graph complex. So that's maybe just to have in the mind how this arises. But this STU squared is something, is a relation that appears really just in this context. And this is just to give you an idea how it looks, but it's really not important for my talk. Okay, but this is the reason that why we don't understand these groups, because when we quotient by this relation, we really don't know what we get. However, what this theorem is telling us is that at least we know that this group of n-1 trivial knots modulo the n-equivalence, so that's a group coming from knots. Rationally, we know that we can describe it completely combinatorially in terms of these graphs. Okay. So somehow the point, so I'm now guiding you somehow to this definition of the grope cobordism, and this is the real inspiration for defining them. Somehow when you had these chord diagrams and Vasiliev invariants, there was a natural interpretation of what a chord should mean geometrically. It really corresponds to a crossing change. So if I give you a chord on the unknot, you can do this crossing changes. If I give you many of them, you can just iterate, do many crossing changes, you get some knot, right? So you can imagine that it can be very complicated. But there is no really meaning in this trivial invertices, which appeared from this perturbative expansions, right? So it's not really a geometric description. They're more of like a bookkeeping tool from that perspective. Okay, so this is how the n-equivalence and the gropes arise. So yeah, one thing I didn't say is that these graphs have degrees. So degree of such a tree is the total number of vertices over 2. Okay, so now I will tell you what a grope cobordism should be. So first of all, if I have such a Jacobi tree, I call it, so a tree modulo those relations, I can pick a root, and then my claim is that picking a root gives me, so a tree with a root is the same thing as such a 2 complex, which is built inductively. So I can just tell you from the examples, because writing out the definition is not really helpful, but just look at this example. So if you have one trivial invertex, you always want to have this bottom stage which has 2 boundary components, and these will correspond to like a cobordism between 2 knots, okay? And so what this genus is, so what this trivial vertex is, the first one next to the root, is that you input some genus here. So you input genus 1, you have this genus 1 surface. This is my interpretation of a trivial vertex. And now how I do it inductively. So I see that here on this genus 1 surface with 2 boundary components, I have these 2 generators of homology, and I think of them here as having as bounding disks. And now when I want to iterate the procedure, so I somehow replace this 1 here, right, which was a disk. You can think of a disk that's like a small cap here, and I replace it by a next level tree. Okay, so I inductively build this by replacing every disk, which I call cap. So for example, in this other example, I don't know if you can see it, but there are like all these leaves correspond to the curves which I haven't killed by attaching higher stuff, right? So they are leftovers. They are still free to attach disks because they don't have higher surfaces attached to them. Okay, so this is the main interpretation of the tree. And here here's the definition. So given such an abstract, so I have a correspondence between rooted trees and abstract gropes. If I want a capped grope cobordism of degree n, then I embed such a thing into my cube. Okay, and you can think, so here in this example, this is the embedding of this guy. You see? So these pictures take some time to parse, but you just remember, from the Morse theory, also the composition of the torus looks like you first have this minimum, then you attach two bands. Okay, and you can see those two bands here. So my bottom stage here, I just have bottom surface and two caps. And here you can see in green, there is a surface of genus 1 and two boundary components. So boundary is this purple, which you see as an unknot, and there is this other boundary, which is some knot. And what I'm saying here is that this knot and the unknot co-bound this cobordism of degree 2, because this is the degree of this tree. And what I also denoted here is cap 1 and cap 2. These are, if you think about these bands, precisely on them you have these curves generating homology. So I have these embedded disks that bound these curves. Okay? And then in terms of this, you can actually define the realization map that I mentioned before.
You're saying that these two disks are bounding the two
Yes.
the two curves in your torus?
Yes. So one of the conditions, well, I'm not very precise here. So embedding, what does it mean to embed this too complex, right? It's not a manifold, but locally it is. You can just embed every of the stages, and you demand that so every higher stage attaches to some generator like that, and then everything that's left not killed by the higher stage, you have to have disks, which in such a nice way, so they are allowed to intersect with this body, with the bottom surface, but only in such intersections, like pink here. Okay? Some more questions? So this was like first part about the grope cobordisms. Now I'm going to switch to the embedding calculus. So what we get from the embedding calculus is such a tower. So in the case of classical knots, we have this codimension 2. Actually, it turns out that the first level of the tower is just emergence, and we have all the sequence. We have this sequence of evaluation maps. So I'll later, if I have time, I'll actually tell you how I think for our theorem, how I think about this T and K. So what we know is that for embeddings of higher codimension, we heard this in Victor's talk, actually this T infinity is equivalent to the original embedding space. But of course, we are precisely in codimension 2. So this result does not hold. However, why we are interested in this is that, well, we get some invariance of knots. And we actually, this is actually, you can prove this is uncountable, but this thing still can be injective. And we have this theorem by Budney-Conant-Koytcheff-Sinha. Yeah, sorry for not writing down the years, but this should be pretty recent, maybe published in 2017, not sure. So there is factorization. So if you take pi 0 of everything, you have this pi 0 evaluation, and actually it factors through this n equivalence. Okay? Precisely these indices match up. Nth level of the tower matches up with this. Okay, so I know this is the last talk today, but just remember we have the wine reception in the bookshop later. So stay with me. So there is this conjecture, and this is somehow the main thing. Why really how this tower connects with Vasiliev theory, and that's precisely the conjecture that this is isomorphism, so that the components of the tower really model your n equivalence. Okay, so here I have this n equivalence defined only on the level of the monoid, on the level of pi 0, but I get the whole space here, which is somehow should be more useful, right? Because we had so many open problems about this theory. Okay, so here's our theorem. So here I fix some tree type with the root. I have the corresponding abstract grope that I showed you how to construct inductively. And then you can consider embeddings, all embeddings of such things. What we do is we have this, that's why I call it extended evaluation map, because we extend this map, which is defined on knots, to a map defined on gropes, and going here to the path space. So the goal is somehow to see this cobordism as a path in T and K. What you get from this is, as a corollary, is the theorem that I mentioned, that these factors, right? Because if two knots are n-equivalent, then when you evaluate them, you have a path, right? And so they must lie in the same connected component. So this is somehow a space level, maybe a statement of this theorem. Okay? So I want to sketch for you, so I promise that there is this geometric trick, how you can think about it. So I'll just sketch how the proof should look like. So we want to construct such an evaluation map. And so what we'll do is we'll consider the punctured knots definition of T and K. I'll give that in the next slide. But let's just observe a couple of things. So what I did here, if you can see the difference, I took this grope. So here, yeah, maybe I should describe this notation. So I always assume from now on that if I have a tree, I will pick the root to be the first. You know, these points are ordered on the line. I can just pick one, and it's somehow breaking the symmetry, but it doesn't really do anything in the end. So I can maybe explain that later. So I fix that this is the root, and so you can see by my construction of the grope, I will actually have such subintervals where I can see that K differs from U. So actually it differs only on J0. So this is the first observation. If you remove this gray part, this is somehow the part of the interval where you map the interval by K and you map by U, they differ. So you see that what's left is completely the same. That's the first observation. The second observation is that we have these, so if you imagine that you fill in this with a cap, you have intersection of that disk with this bottom surface, okay? And they are really, so you have one such for every leaf that you had in a tree, okay? So that's how this n comes into the story. So you'll have something of degree n, a grope of degree n, but you also have T and K. What I say here is that on the complement, so if you remove this little interval J1, then you can see that this band can somehow be isotoped back. And actually everything else will also isotope to the unknot. Somehow it completely unravels once you remove this intersection with the cap. So caps are really measuring that. How far is your knot from being isotopic to the unknot. Okay? And what else? So here is a abstract picture. So if the first picture is too complicated, you can just think of this. So just think of this. You have the two disks attached to these circles, and you can do surgery on both of them. And these are the results you obtain. So, but what I want to do is I want to do this ambiently. So I actually have embedded disks, and I can do surgery ambiently on those disks. But I can do it only if that intersection is not there. So once I remove the intersection with the cap, I can do the surgery. And this is the statement that somehow it seems that different surgeries are isotopic. So you can do one for each of the caps, right? If you do surgery on one cap, you're not completely, you can isotope it to the unknot, but you can actually do this for every cap that you have. And this is the way to see a homotopy limit, I claim. Okay, so here's the definition of Tn. This is maybe the simplest definition. So if you haven't seen embedding calculus, I think this is a good starting point. You can fix a sequence of subintervals of the closed disjoint of the interval. And okay, of course, this works just if your domain is already interval. And you I consider for every subset of the set of points of set of 0 to n, I consider the S-punctured interval. So I take out precisely those subintervals indexed by S. And then I considered what I call here S-punctured knots. So knots, so they're not really knots because they have these punctures, but they are embeddings of everything else, of the complement. And then you see that for every non-empty S, you can consider this functor from a cube. This is a punctured cube. So these subsets form a cube. You just don't consider S equal to empty set. And then you take a homotopy limit over that cube. Okay? And because you punctured the cube, you always have the map from the limit, right, from the empty set. So this is my definition of Tn. Are there questions about that? Yeah, so now I'll tell you a bit about the proof. So here is somehow the main, like I would say, technical part. Everything else is somehow just untangling what the definitions are of these things. So what we do is, I told you that there are all these isotopies for different caps. And we just want to put them in this one nice map. So there is this map HG, parameterized by a simplex, which for each point in the simplex, this is an embedding disk, which has, so delta 0 and delta 1 are two boundaries. So remember, in our grope, we have this bottom surface which has two boundaries. So this is delta 0 and delta 1. Okay, so we want this family of disks. And how will this imply the theorem? Well, you can use this interpretation of the homotopy limit over the cube as the mapping space of, you take the classifying space of this category. So for each k, you have the overcategory of a cube over k. And actually, this turns out just to be, again, a category built out of these simplices. A cube built out of the simplices. So in order to specify such an element of T and K, you just want a collection. So for each S, and in this cube, so a non-empty subset of n, you want a map from delta S to these S-punctured knots. Right? So that's what I need to specify. I actually want to specify a path in this space. So I want to specify, so evaluation of a grope G will be a one-parameter family of such collections. Okay? So here's actually the last slide. So what does this mean? Well, actually, if you remember my first observation, when I removed this subinterval J0, I had something that's already isotopic to the unknot. So I could just keep it fixed there. Actually, sorry, not isotopic, but it was really the same. It was, when you remove this gray part, they were really the same. Okay, and for each other S, we have to specify what, so here is one example for a degree of the group 2. So these should be, these are just bottom surfaces. You have this triangle, so this is this realization of the cube that we're looking at. So for everything that includes 0, I just keep it constant. So what do these indices mean? If you go to the previous slide, so here, right, you're looking at a map from delta S. Here I mean, oh, sorry, I maybe didn't write. So delta S means delta to the number of elements in S, right? So if I have, so these are different S's, 0, 1, 2, and then you have 1, 2, 0, 2, etc. So whenever 0 appears in your set, that means that you punctured a knot at your J0. So they are the same. The knot and the unknot are the same. So you want to keep that constant. However, on these other non-zero S's, so S's that don't contain 0, you actually want to use these caps as guides for your isotopies. And that's what you do. So I denoted here blue. So this is this blue generator. So here, maybe in this picture, you have this blue curve. You can do the surgery. When you do the surgery, you have two copies of the disk, and this basically determines an isotopy between these two knots. You can do the same with the other cap, and then what you need to do is actually you need to define this whole simplex, right? You need a one-parameter family of isotopies. And this is the geometric trick that I announced at the beginning. It actually turns out that if you have an embedding grope and if you plug in, so just think of these caps, you thicken them a bit and they look like plugs that you just plug into all the holes in the grope, and that what it becomes is really a 3-ball. And that 3-ball is nicely, because the degrees match up, it's actually parametrizing. So in this example it's degree 2, so it's really one family of disks, one parameter family of disks. So what I claim is that there is a family of disks between a blue and a green, along which I can do isotopies. So in this particular example, this looks like this is actually the same if you plug in these plugs as 3-ball, and this is what will give the map H. Okay, so that's it.
Any questions?
Yeah. Yeah, that's like if you didn't get anything from my talk, you should think that this is how what gropes measure. It measures somehow how much your knot, this red thing, is knotted around. It's my it's really a sketch of how you can think about it, but more precise pictures were before. Yeah.
What is a natural generalization to higher dimensions? Which type of knots, which dimension of knots and which type of Euclidean space would it generalize to?
So I don't know. I think it's most natural for interval, because then only there you have this very particular description of T and K in terms of these punctured intervals. You have this order on the interval, and somehow you lose that for higher dimensional things. Yeah. Mm-hmm.
So you mentioned before that as a corollary of your theorem you get Max-Planck theorem.
Yes.
You also had conjecture there.
Well, we don't get a conjecture, not yet, but yeah. So here is the conjecture. So conjecture is really, I mean, it's often stated that this is a universal invariant of type n, less than n. So I think we are coming closer to understand what these spaces T and K are. So hopefully we'll be able to figure it out, but we're really far from that. So I say in my last slide, so actually I have some questions. And so these are maybe possible questions, and actually I'm working as a part of my thesis also on this, the question whether these maps are surjective. So that would be the first, right? We need isomorphism, so this would imply surjectivity. Yeah.
Is that factorization,
Mm-hmm.
the theorem that
Yeah.
you're talking about, is it known to be rationally equivalent?
Yeah, I think it follows by combining all these, like this rational result at the beginning and some results about the rational collapse, which follow, for example, from the paper of Frass, Turchin, Willwacher. So using somehow, in that case, you can actually compare these hairy graphs to the graphs that I mentioned, and then you can get it. Yeah. So, but we're somehow after this integral statement.
Any other questions?